This video is about determining the period of a hysteresis oscillator. It corresponds to section 16.3 of Applied Analog Electronics. Now, the problem is to figure out for this circuit, where we just have an inverting Schmitt trigger, charging a capacitor through a resistor, or discharging the capacitor through the resistor. This thing oscillates because when the output is high, we charge the capacitor until we get to the upper threshold of the Schmitt trigger, in which case the Schmitt trigger switches to putting in low output, and then we discharge the capacitor until we get down to the lower threshold of the Schmitt trigger, and then the output of the Schmitt trigger changes again to being high, and we start charging the capacitor again. So the main things we're looking at here are charging curves, RC charging curves for that resistor and that capacitor. And we have both a charging curve and a discharging curve. Here I've assumed the Schmitt trigger is powered by a 5-volt power supply, so the high voltage of the output is 5 volts, and the low voltage of the output is 0 volts. So the blue curve there is the discharge down to 0 volts, and the sort of brownish curve is charging up to 5 volts. And the two horizontal lines across there represent the two thresholds for the Schmitt trigger. And we don't actually use the whole curve here, because the moment we cross the light blue line with the blue discharge, we're going to stop discharging. The output of the Schmitt trigger is going to change, and we'll switch over to charging. And similarly, when we cross the yellow line, charging on the brown curve, then we're going to again switch the output of the Schmitt trigger and start discharging. So let's take a look at what that looks like here. Here I've drawn the charging and discharging curves, and between the two thresholds is the waveform that we actually get. It charges from the low threshold up to the high threshold, then the output switches and we discharge from the high threshold down to the low threshold, which means the output changes to high, and we start charging again. And then hit the threshold, switch the output to low and start discharging, and so on back and forth. And so in order to determine the period here, how long does it take to do a full cycle, we need to look at how long does it take to charge from the low threshold to the high threshold. That's sort of that black line highlighted in yellow, plus how long does it take to discharge. That's the black line highlighted in blue. And if you look at the picture here closely, you'll see that the charging time and the discharging time aren't necessarily the same. It has to do with where the thresholds are and where the output voltages are, and you can get quite a bit of asymmetry between the charging and the discharging here. So now what we need to do is come up with a formula for figuring out how long does it take to charge, how long does it take to discharge. Add the two together to get the period. Now I'm only going to do half the problem for you. I'm going to show you how to do the charging one from the input low threshold to the input high threshold. That's the yellow highlighted line here. You're going to have to do the blue one yourself. It's a very similar calculation. If you understand the calculation for doing the yellow one, the blue one is straightforward. It's going to give you a different number because there is an asymmetry. But the derivation is done in exactly the same way. So let's take a look at what that derivation is. First thing we need is, what is the formula for a capacitor charging or discharging? And we had that back in section 11.4, and it was done as the voltage on the capacitor minus the eventual voltage, the one on the other side of the resistor, is equal to the initial voltage minus that eventual voltage times e to the minus t over RC. So that's where the RC time constant comes in. That's the general formula for any sort of charge-discharge. Now, I was going to be looking at that yellow curve charging up, starting at V0 being the input low threshold. And what was I charging to? Well, V infinity that's the voltage on the other side of the resistor. That's going to be whatever the output high is. For the example I was looking at, that was 5 volts. You could do this symbolically if you want to do it for different voltages, like if you want to run a 3.3 volts or a 2.7 volts or whatever you want to put on your Schmidt trigger, the output high voltage, whatever it is. Okay, so we have what V0 is, we have what V infinity is, we know RC. We've got basically the entire formula here for how voltage changes as a function of time. But we weren't interested in plotting out the entire thing. Well, maybe you are sometimes, but what we were specifically interested in is how long did it take to get from that initial input low up to input high. So what we want to know is for what t is V of t equal to the other threshold, VIH. And to do that, we can just plug in here and rewrite. So we have VIH minus V infinity equals V0 minus V infinity e to the minus t over RC. All right. And we were interested in what t is, so we just need to do a little bit of algebra here, divide both sides by v0 minus v infinity, take logs, and so forth. So we're going to have VIH minus v infinity over v0 minus v infinity. Take the natural log of that, and that's going to be minus t over RC. All right, and since we just want t, multiply both sides by RC, and negate both sides. And little trick here, when you negate a logarithm, that's the same thing as taking the logarithm of the multiplicative inverse. So we can write this thing as t equals RC times the natural log of, and now we flip this fraction upside down. Oh, I shouldn't have written this as V0 and V infinity. I should have written that V infinity was VOH. And V0 was VIL. Okay, so flipping that upside down, we have VIL minus VOH over VIH minus VOH. And that is the time for the yellow curve here, the charging up from VIL to VIH. You can do a similar sort of calculation to get the curve coming down. There is another way to do these estimates. Instead of doing these exponential charging curves, you could do something much cruder where you just say, let's pretend that the voltage on the capacitor is basically constant. Just take the average value of the voltage on the capacitor, and how much current do we get through the resistor then? So we're just, instead of looking at the actual current through the resistor, we just say, what's the average current through the resistor? And it's either positive or negative, so we're either discharging or charging. That's what we would get if we were doing a proper triangle wave here. And so it's kind of a crude approximation. This thing doesn't really have a straight line for the two parts of the triangle wave, but you can approximate it as that, and that gives you, you can look in the book, a very simple formula that's actually simpler than this stuff with the logarithms. It turns out that neither model is completely accurate because we've ignored some phenomenon with a Schmidt trigger. And as a result, it doesn't really matter too much which of these two models you pick. They're both somewhat inaccurate, and they're both good enough. So pick which one you like and apply it to get both the charging and the discharging time to get an estimate of the period. If you go back and look at this formula here, you notice that this period is proportional to RC, because we're going to have RC times a constant here that depends on the thresholds and the output voltages. You're going to get a similar formula, slightly different, for the discharge time. When you add them together, you'll get, again, the RC time constant times some constant that just depends on what the threshold voltages and the input high and the output high and output low voltages are. So the period is going to be proportional to the RC time constant, but it's not equal to the RC time constant. This is a mistake that a lot of students make, is just say, oh, I've got the RC time constant, and that's going to tell me the period. what you've got is something proportional to period. Now, the constant proportionality may not be very far from 1, in which case, you can say, oh, this is just good enough to just get the RC time constant, but it might be quite a ways from 1. It depends a lot on what all these specific values are. And so do go through and do the calculation properly to see what period you expect from your hysteresis oscillator.